Hello, I'm Pramod Prasad from EMC Education Services. Welcome to this online learning session in which I will present an introduction to object-based and unified storage. In object-based storage, data is stored in the form of objects instead of in the form of blocks or files. In unified storage, block, file, and object-based data access are consolidated within one unified platform. In this session, I will talk about object-based and unified storage, their components, and the data access processes in the two. So what are the objectives of this session? Upon completion of this session, you should be able to describe object-based storage model, list the key components of object-based storage, describe the storage and retrieval process in object-based storage, describe content addressed storage, list the key components of unified storage, and describe the process of data access from unified storage. Drivers for object-based storage. Let's begin by understanding the need for object-based storage. Studies have shown that more than 90% of digital data that is generated is unstructured. The growth of unstructured data poses several challenges to IT administrators and storage managers. With this growth, traditional network-attached storage or NAS, which is a dominant solution for storing unstructured data, may be inefficient. Data growth adds high overhead to the NAS in terms of managing a large number of permissions and nested directories. In an enterprise environment, NAS also manages large amounts of metadata generated by hosts, storage systems, and individual applications. Typically, the metadata is stored as part of the file and distributed throughout the environment. This adds to the complexity and latency in searching and retrieving files. Thus, a need emerged for a smarter approach to manage unstructured data based on its content rather than the metadata about its name and location and so on. Object-based storage is a way to store file data in the form of object based on its content and other attributes rather than the name and location. What is object-based storage? Object-based storage is a way to store file data in the form of objects on flat address space based on content and attributes rather than the name and location. Object-based storage uses an object-based storage device or OSD to store data. An OSD is a device that organizes and stores unstructured data such as videos, documents, and images as objects. Object-based storage provides a scalable, self-managed, protected, and shared storage option. OSD uses a flat address space to store data in the form of objects. Therefore, there is no hierarchy of directories and files. As a result, a large number of objects can be stored in an OSD system. An object might contain data, related metadata such as size, date, ownership, etc., and other attributes of data such as retention and access pattern. Each object stored in the system is identified by a unique ID called the object ID. The object ID is generated using specialized algorithms such as hash function on the data and guarantees that every object is uniquely identified. Hierarchical file system versus flat address space. The slide shows how data is organized in an hierarchical file system and a flat address space. A hierarchical file system organizes data in the form of files and directories. Object-based storage uses flat address space, wherein each object has a unique object ID and contains the data, metadata, and other attributes. Traditional versus object-based storage model. An I/O in the traditional block access method passes through various layers in the I/O path. The I/O generated by an application passes through the file system, the channel or network, and reaches the disk drive. When the file system receives the I/O from an application, the file system maps the incoming I/O to the disk blocks. The block interface is used for sending the I/O over the channel or network to the storage device. The I/O is then written to the block allocated on the disk drive. The file system has two components, user component and storage component. The user component of the file system performs functions such as hierarchy management, naming, and user access control. The storage component maps the files to the physical location on the disk drive. When an application accesses data stored in OSD, the request is sent to the file system user component. The file system user component communicates to the OSD interface, which in turn sends the request to the storage device. The storage device has the OSD storage component responsible for managing the access to the object on a storage device. After the object is stored, the OSD sends an acknowledgement to the application server. The OSD storage component manages all the required low-level storage and space management functions. It also manages security and access control functions for the objects. Key components of OSD. The OSD system is typically composed of three key components: nodes, private network, and storage. The OSD system is composed of one or more nodes. A node is a server that runs the OSD operating environment and provides services to store, retrieve, and manage data in the system. The OSD node has two key services: metadata service and storage service. The metadata service is responsible for generating the object ID from the contents of a file, and in some cases may also include other attributes of data. It also maintains the mapping of the object IDs and the file system namespace. The storage service manages a set of disks on which the user data is stored. The OSD nodes connect to the storage via an internal network. The internal network provides node-to-node connectivity and node-to-storage connectivity. The application server accesses the node to store and retrieve data over an external network. In some implementations, such as a content address system, the metadata service might reside on the application server or on a separate server. OSD typically uses low-cost and high-density disk drives to store the objects. As more capacity is required, more disk drives can be added to the system. Process of storing object in OSD. The process of storing objects in OSD is illustrated on this slide. The data storage process in an OSD is as follows. In step 1, the application server presents the file to be stored to the OSD node. In step 2, the OSD node divides the file into two parts: user data and metadata. In step 3, the OSD node generates the object ID using a specialized algorithm. The algorithm is executed against the contents of the user data to derive an ID unique to this data. In step 4, the OSD node stores the metadata and object ID for future access using the metadata service. In step 5, the OSD node stores the user data, that is objects, in the storage device using the storage service. Finally, in step 6, an acknowledgement is sent to the application server stating that the object is stored. Process of retrieving object from OSD. After an object is stored successfully, it is available for retrieval. A user accesses the data stored on OSD by the same file name. The application server retrieves the stored content using the object ID. This process is transparent to the user. The process of retrieving objects in OSD is illustrated on the slide. The process of data retrieval is as follows. In step 1, the application server sends a read request to the OSD system. In step 2, the metadata service retrieves the object ID from the requested file. In step 3, the metadata service sends the object ID to the application server. In step 4, the application server sends the object ID to the OSD storage service for object retrieval. In step 5, the OSD storage service retrieves the object from the storage device. Finally, in step 6, the OSD storage service sends the file to the application server. Key benefits of object-based storage. For unstructured data, object-based storage devices provide numerous benefits over traditional storage solutions. An ideal storage architecture should provide performance, scalability, security, and data sharing across multiple platforms. Traditional storage solutions such as SAN and NAS do not offer all these benefits as a single solution. Object-based storage combines benefits of both the worlds. It provides platform and location independence and at the same time provides scalability, security, and data sharing capabilities. The key benefits of object-based storage are as follows. Security and reliability. Data integrity and content authenticity are the key features of object-based storage devices. OSD uses specialized algorithms to create objects that provide strong data encryption capability. In OSD, request authentication is performed at the storage device rather than with an external authentication mechanism. Platform independence. Objects are abstract containers of data, including metadata and attributes. This feature allows objects to be shared across heterogeneous platforms locally or remotely. This platform independence capability makes object-based storage the best candidate for cloud computing environments. Scalability. Due to the use of flat address space, object-based storage can handle large amounts of data without impacting performance. Both storage and OSD nodes can be scaled independently in terms of performance and capacity. Manageability. Object-based storage has an inherent intelligence to manage and protect objects. It uses self-healing capability to protect and replicate objects. Policy-based management capability helps OSD to handle routine jobs automatically. Cloud-based storage. Cloud-based storage is a promising use case of OSD. OSD uses a web interface to access storage resources. OSD provides inherent security, scalability, and automated data management. It also enables data sharing across heterogeneous platforms or tenants while ensuring integrity of data. These capabilities make OSD a strong option for cloud-based storage. Cloud service providers can leverage OSD to offer storage as a service. OSD supports web service access via representational state transfer or REST and simple object access protocol or SOAP. REST and SOAP APIs can be easily integrated with business applications that access OSD over the web. Content address storage. Content address storage or CAS is a special type of object-based storage device purposely built for storing fixed content such as data archives. Data integrity and protection is the primary requirement for any data archiving solution. Traditional archival solutions such as using devices such as CD and DVD-ROM do not provide scalability and performance. OSD stores data in the form of objects, associates them with a unique object ID, and ensures high data integrity. Along with integrity, it provides scalability and data protection. These capabilities make OSD a viable option for long-term data archival of fixed content. CAS is an object-based storage device designed for secure online storage and retrieval of fixed content. CAS stores user data and its attributes as an object. The stored object is assigned a globally unique address known as a content address or CA. This address is derived from the object's binary representation. CAS provides an optimized and centrally managed storage solution. Data access in CAS differs from other OSD devices. In CAS, the application server can access the CAS device only via the CAS API running on the application server. However, the way CAS stores data is similar to the other OSD systems. Key features of CAS. CAS provides all the features required for storing fixed content. The key features are as follows. Content authenticity. This assures that the genuineness of stored content is achieved by generating a unique content address for each object and validating the content address for stored objects at regular intervals. Content authenticity is assured because the address assigned to each object is unique. Every time an object is read, CAS uses a hashing algorithm to recalculate the object's content address as a validation step and compares the result to its original content address. If the object fails validation, CAS rebuilds the object using a mirror or parity protection scheme. Content integrity. It provides assurance that the stored content has not been altered. CAS uses a hashing algorithm for content authenticity and integrity. If the fixed content is altered, CAS generates a new address for the altered content, rather than overwrite the original fixed content. Location independence. CAS uses a unique content address rather than directory path names or URLs to retrieve data. This makes the physical location of the stored data irrelevant to the application that requests the data. Single instance storage. CAS uses a unique content address to guarantee that the storage of only a single instance of an object. When a new object is written, the CAS system is polled to see whether an object is already available within the same content address. If the object is available in the system, it is not stored. Instead, only a pointer to that object is created. Retention enforcement. Protecting and retaining objects is a core requirement of an archive storage system. After an object is stored in the CAS system and the retention policy is defined, CAS does not make the object available for deletion until the policy expires. Data protection. CAS ensures that the content stored on the CAS system is available even if a disk or a node fails. CAS provides both local and remote protection to the data objects stored on it. In the local protection option, data objects are either mirrored or parity protected. In mirror protection, 2 copies of the data object are stored on 2 different nodes in the same cluster. This decreases the total available capacity by 50%. In parity protection, the data object is split into multiple parts and parity is generated from them. Each part of the data and its parity are stored on a different node. This method consumes less capacity to protect the stored data, but takes slightly longer to regenerate the data if corruption of data occurs. In the remote replication option, data objects are copied to a secondary CAS at a remote location. In this case, the objects remain accessible from the secondary CAS if the primary CAS system fails. Fast record retrieval. CAS stores all objects on disks, which provides faster access to the objects compared to tapes or optical disks. Load balancing. CAS distributes objects across multiple nodes to provide maximum throughput and availability. Scalability. CAS allows the addition of more nodes to the cluster without any interruption to data access and with minimum administrative overhead. Event notification. CAS continuously monitors the state of the system and raises an alert for any event that requires the administrator's attention. The event notification is communicated to the administrator through SNMP, SMTP, or email. Self-diagnosis and repair. CAS automatically detects and repairs corrupted objects and alerts the administrator about the potential problem. CAS systems can be configured to alert remote support teams who can diagnose and repair the system remotely. Audit trails. CAS keeps track of management activities and any access or disposition of data. Audit trails are mandated by compliance requirements. The use case of CAS is in healthcare. Large healthcare centers examine hundreds of patients every day and generate large volumes of medical records. Each record might be composed of 1 or more images that range in size from approximately 15 MB for a standard digital X-ray to more than 1 GB for oncology studies. The patient records are stored online for a specific period of time for immediate use by the attending physicians. Even if a patient's record is no longer needed, compliance requirements might stipulate that the records be kept in the original format for several years. Medical image solution providers offer hospitals the capability to view medical records such as X-ray images, with acceptable response times and resolution to enable rapid assessments of patients. Patient records are retained on the primary storage for 60 days, after which they are moved to the CAS system. CAS facilitates long-term storage and at the same time provides immediate access to data when needed. A second use case of CAS is in finance. In a typical banking scenario, images of checks, each approximately 25 KB in size, are created and sent to archive services over an IP network. A check imaging service provider might process approximately 90 million check images per month. Typically, check images are actively processed in transactional systems for about 5 days. For the next 60 days, check images may be requested by banks or individual consumers for verification purposes, and beyond 60 days, access requirements drop drastically. The check images are moved from the primary storage to the CAS system after 60 days and can be held there for long term based on retention policy. Check imaging is one example of a financial service application that is best serviced with CAS. Customer transactions initiated by email, contracts and security transaction records might need to be kept online for 30 years. CAS is the preferred storage solution in such cases. Drivers for unified storage. Due to varied application requirements, organizations have been deploying storage area networks, SANs, NAS, and object-based storage devices in their data centers. Deploying these disparate storage solutions adds management complexity, cost, and environmental overheads. An ideal solution would have an integrated storage solution that supports block, file, and object access. Unified storage has emerged as a solution that consolidates block, file, and object-based access within one unified platform. It supports multiple protocols for data access and can be managed using a single management interface. Components of unified storage. A unified storage system has the following key components: a storage controller, NAS head, OSD node, and storage. The storage controller provides block level access to application servers through iSCSI, FC, or FCOE protocols. It contains iSCSI, FC, and FCOE front-end ports for direct block access. The storage controller is also responsible for managing the back-end storage pool in the storage system. The controller configures LUNs and presents them to application servers, NAS heads, and OSD nodes. The LUNs presented to the application server appear as local physical disks. A file system is configured on these LUNs and is made available to applications for storing data. A NAS head is a dedicated file server that provides file access to NAS clients. The NAS head is connected to the storage via the storage controller, typically using FC or FCOE connection. The system typically has 2 or more NAS heads for redundancy. The LUNs presented to the NAS head appear as physical disks. The NAS head configures the file systems on these disks, creates an NFS, CIFS, or a mixed share, and exports the share to the NAS clients. The OSD node accesses the storage through the storage controller using an FC or FCOE connection. The LUNs assigned to the OSD node appear as physical disks. These disks are configured by the OSD nodes, enabling them to store the data from the web application servers. Data access from unified storage. In a unified storage system, block, file, and object requests to the storage travel through different I/O paths. Block I/O request. The application servers are connected to an FC, iSCSI, or FCOE port on the storage controller. The server sends a block request over an FC, iSCSI, or FCOE connection. The storage controller processes the I/O and responds to the application server. For file I/O request, the NAS clients sends a file request to the NAS head using the NFS or CIFS protocol. The NAS head receives the request, converts it into a block request, and forwards it to the storage controller. Upon receiving the block data from the storage controller, the NAS head again converts the block request back to the file request and sends it to the clients. For object I/O request, the web application servers send an object request, typically using REST or SOAP protocols, to the OSD node. The OSD node receives the request, converts it into a block request, and sends it to the disk through the storage controller. The controller in turn processes the block request and responds back to the OSD node, which in turn provides the requested object to the web application server. So in this session, we covered object-based storage model and its key components. We covered the process of storage and retrieval in object-based storage. We covered unified storage and its key components. Finally, we covered the process of data access from unified storage. That brings us to the end of this session on Introduction to Object-Based and Unified Storage. Thank you for watching.